All right, here we go. The normal distribution, chapter 7, our last two lessons. We began by discussing data, which is distributed normally. And what does that mean? We're going to use a couple symbols, which we've talked about in the past. Hopefully you know what the X bar, that means the mean. And hopefully you remember what the sigma, lowercase, it is the standard deviation. Those symbols will start popping up. Ooh, another one that they are going to use sometimes is mu, which is the other symbol for the mean. Okay. It's just a lowercase u script. And our question kind of today is, what is normal? Am I normal? Is my data normal? Can I expect it to be normal? Well, if the answer to those questions is yes, yeah, here is kind of what that graph is going to look like. By the way, sometimes they call this the density curve. Sometimes they call it the bell curve. So it goes by various names. A couple things about this graph. Number one, there's no skew. So when I graph this data, and again, it's going to look like this shape. Notice there is a symmetry to this shape. The left and the right are identical. Yeah, so we say it's symmetric. Second of all, notice this is not just like 20 people that are gathered together, but rather data, a large number, hundreds, thousands of data points. And that gives us confidence that in fact we are looking at what we would call a normal distribution, where most of the people are going to be near the middle. And you can define that middle to be any, like any quantity that you want. It could be the average height, weight, average age, IQ, all these different things, right? Again, we're going to say use the mean symbol, X bar. Again, we could also say mu. So that area we're going to talk about that lives between here, the curve, and that x-axis, that area is everything. It's the whole population, okay? And so, therefore, we will represent it as 100 or 1. Okay? So that's the area, as we say, under the curve. Now, we need to break that area up. First of all, cut it in half like I did with the mean. Then we're going to draw some other lines to break it into different categories. These lines will be separated by equal amounts. First of all, how do I know where to draw the first line? Well, there is very fancy explanations to explain this cutoff point right there, approximately right there. Okay, I'm using my eyeball to kind of guess where it's at. Is what we would define as the first standard deviation. So I'm going to say +1, and then I'm going to use the standard deviation to the right of the mean. And that distance there, think of that little horizontal distance, now is my distance that I'm going to use to describe all my other breakpoints in the data set. A couple things, well, mainly one thing, the area between the first standard deviation and the mean is 34%. So 34% of my data lives in that region. Since it's symmetric, I'm going to go to this side and do the same thing and cut it off here, yeah, and call that -1 standard deviations to the left. And again, it too will have 34% of the data. Notice that when you add 34 and 34, you get 68. And this is what we would call this rule that we're going to use down here in a moment. call the 68, 95, 99.7 rule. All right. Now again, using that same horizontal distance, okay, I'm now going to move to the right again and make another point, roughly, right there. And that'd be +2 standard deviations. And then I want to do the same symmetrically on this side. So come up there, come down, and that would be -2 standard deviations. And now the area under this new region is smaller, as you can see. Precisely, we know that the area is 13.5% of the population. That is between 1 and the second standard deviation. We should technically, like, graph that with a different color, yeah? So this is now a new region. Make sense? Okay, so that's 13.5% of the population there. All right, then I'm gonna go out a third standard deviation. And bam. Again, we're just eyeballing. We have technology that will actually draw this out. We could figure that out. But that would be the new area here is 2.35. Had to turn around and look behind me because this one I don't have memorized. It's a very small portion of the population. And likewise on this side, forgot to mark that, it's -3 standard deviations away. So this is +3 standard deviations away. From the mean is 2.35. Sometimes those spaces get kind of small, so then I just put it outside. All right, so that is the 3 categories to the left and to the right of the mean, and kind of what they represent of the data. Now, if I add those up, how much data is encompassed in the first standard deviation? Well, 34 and 34 is 68%. Now, if I take then the 13.5, okay, 34 times 2, so 13.5 times 2 is 27, yeah, and I add that to the 68, then I get 95% of the data is living within 2 standard deviations. Okay. Again, we are looking at what we would call the first 2. So that would be everything from here to here, 95. And then if I go out for 3 standard deviations, right, that would then be adding the 2.35, doubling it, times 2. I think I get 4.7. So then we have 99.7% of the population. Okay? All right. Now we're going to use that data to solve some problems, and that's basically your homework. You're learning to use those numbers and the standard deviations and the means to calculate what percent of the population lives in that region. So the first problem here involves the SAT exam, and the standard deviation is 100 and the mean is 500. So we're going to sketch the curve with the cutoffs for the first part of the problem. And that's just going to help us be able to do the rest of the questions, so to speak. So learning to draw and sketch this curve, kind of important for this last 2 units. In the middle, again, would be the mean, in this case 500. The standard deviation is 100, so to the left and right of that then, if I look at 1 standard deviation away, that would be 600 and then 400. Again, if I go a second standard deviation away from that, that would give me the 700 cutoff and the 300 cutoff. And finally, nearly the whole population, right? 99.7% will be between 800 and 200. Okay? There's going to be the odd student that is above and below those, but that's not our concern at this point. All right, we got the sketch made. Now we are going to answer how many have a score of at least 600. Okay. Well, here's the 600, and at least would be everything below that. So for this problem, I need to add the region, this region, plus this region, plus this region, plus this region. So I'm going to say 34 times 2, or 68, right? Plus the 13.5, plus the 2.35. All right, and that tells me, according to my TI calculator here, 90, no, I didn't do that right. 68 plus 13.5 plus 2.35. All right, at 83.85% of my population. All right. Now, suppose 4,600 students take the exam. Oh, hang on. That was part B. I got to do part C. Between what two scores did the middle 95% of the students score? Now, you recall the 95% is one of my special categories, right? 95% would be the number of people that are 2 standard deviations away. So that would be this group. And so that would be between 300 and 700. So between 300 to 700. Now, how many would score at least 700 if 4,600 students took the exam? Okay, so no percents. Cross those percent symbols off. The score is 700. All right, so how many would score at least 700? So I need to come out here and grab, so there's 700, right? And I need to add all those. Okay, so I need to add 2 34s, so 34 times 2. Plus 13.5 times 2 times 2 plus, and then I need 2.35. All right, so 68 plus 27 plus 2.35. So 68 plus 27 plus 2.35. 97.35. 97.35% of the population have a score of at least 700. Well, how about more than 700? Well, that would be the rest of the population, correct? So to find out this population, I'm just going to take this number and subtract it from 100. Okay, so 100 minus 97 point, what did I say? It's 35. Is 2.65%. Okay? Last question. As we do this type of data, one of the questions in the back of the mind is the data that we've collected normally distributed? And if we look at the SAT score, can we expect most of the people, students who take this exam, to be in the middle, with some students to the right and some students to the left of that? And you can make arguments, yes, for that quite convincingly. So I think normally with IQ tests, we can see this type of distribution. So therefore, you can do that with generally exam scores. That happens. Now, not all populations you can do that. In class, we did a shoe population, shoe size, and we saw that unfortunately, this part of the population doesn't live in our classrooms. Instead, we have a right skewed graph. And that's because shoe sizes, your feet are still growing while you're a teenager and they're not done. And so some people have grown faster, and a few of them have, but you don't have that tail end because it isn't like people have really tiny feet. Now, if you look at normal adults, they will actually have a greater distribution, a more even distribution, because there is that, okay? What about the heights of all Americans? Would that be a normal distribution? What about the wingspan of 3-year-old eagles, if I collected those? What about the number of teeth? Would these be normal? Well, only one of them is. The others, they won't. They're gonna have problems. Hopefully you've had time to guess one of them. Is it the number of teeth the average American has? And that is no. Nearly everybody has, I forget, 32 teeth, I think it is. You can double check me on that. And so some people are missing a tooth, like Mr. Larson, and therefore it would be skewed to the left. It would be kind of like this. That would be that distribution, right? You're not gonna have, well, maybe there is somebody with 33 teeth. Like you got an extra one. I think my daughter had an extra tooth in her mouth initially, which they removed, but anyways, that happens. What about the heights of adults? You would think that would be a normal distribution. But notice here we have categories of male and female, so you could actually have a bimodal distribution, where you'd have like 2 different heights, right? You could even have different cultural, like South Americans versus North Americans, like they don't necessarily have similar heights. So this would be no. Number one, there is male and female differences that you would need to do out. You certainly could look at any one of those, like male Americans, and try to make an assumption there that there would be a normal distribution. What about the wingspan of 3-year-old eagles? And eagles, that's actually a mature eagle, an older eagle. And so yes, you will find this would be expected to be a normal distribution. And you don't need to know anything about eagles. You just need to know that a 3-year-old is not a juvenile eagle, right? It's no longer growing its wingspan. So those are tricky questions, and you need to kind of think about the problem and think about what types of characteristics are in those sets of data. All right, in your homework, make sure you sketch it out, draw it out. Best of luck in your homework as you do 7